everyone, this is AJ from the Engineering Design Club at Kenyatta College, and I'm here to talk to you about electricity and really what it is, and different aspects that have to do with electricity. So let's get started with a little bit of chemistry. A lot of things that have to do with electronics kind of start with chemistry. So first let's talk about electric charges. Well, as if you've taken chemistry in high school or in college, you know that matter is composed of atoms, and each atom has kind of 2 or 3 different main subatomic particles. You have the protons and neutrons that live inside the nucleus, and that's represented right here in this picture. And you also have these outer electrons that are orbiting, I guess you could say, around the nucleus, right? And the charges, or the subatomic particles, they all have a charge, and that charge is denoted with the character Q, or sometimes it's a big Q, but the protons, which are these white guys in this picture, they have a positive charge. So that's just something that we assigned to protons. They have positive charges. And electrons as well, they have a negative charge. And as you can see in this picture, they have a kind of a negative sign. Alright, and so these negative charges are kind of swarming around this positively charged nucleus. The neutrons, just like its name, doesn't have any charge. It's neutral charge, so it has a charge of 0. So protons have a positive charge and electrons have a negative charge. Alright, so there's a lot of energy that's required to kind of move these particles outside their atomic structure. So in this case, it's really difficult to get these protons that are in this nucleus. If I want to break a proton off, that requires excessive amounts of energy. But what's much easier to do is move these electrons off their orbits. They're already kind of moving in itself, so to get them to break off is far easier, especially since as they go further and further outward, away from the nucleus, those become easier and easier to break off. So in this case, there's an electron in this picture that is now going to break off and just kind of be in the material just as a free electron. And so the electrons in this outermost layer, those are usually given the name valence electrons. And so these valence electrons are, depending on the material, easy to break away from their orbit. All right. So let's start talking about different materials that we will be working with. One of them is a type of material called a conductor, and a conductor is kind of a large category of materials. So these conductors, one of the really big qualities that we will be utilizing is that they allow electrons to move easily. So in these 2 pictures, these are 2 examples of different conductors. We have copper and we have silver over here. Silver atom. Okay. And just in general, in order to get an electron to move, more likely than not, these conductors, it means that in order for these electrons to move easily, usually they have like 1 or 2 valence electrons. So if you notice in these materials that we have, in these outermost layers, there's 1 valence electron in this outer electron shell. So this would be like the valence shell, or valence orbit, or valence shell, whatever you want to call it, shell/orbit. And you notice in that outer layer, the outer shell, there's only one little electron in this copper atom. And if we look over here towards silver, this kind of darker area right here is kind of the outer ring. And once again, if you notice in this silver atom, there's again only one valence electron in that outer valence shell. Valence electron. And the types of materials that have, one or two valence electrons are usually metals, are metals. And so a lot of times these are used to move electricity. What electricity is basically the movement of these electrons. So if you have materials that electrons can move really easily and break away really easily, then that means that these are good conductors of electricity. And many times these are the metals, transition metals. So and when you have a bunch of these atoms put together and you have a bunch of these free electrons just floating there, you have like a bunch of electrons just floating there, that turns into a term that we like to call a sea of electrons. And so they're kind of just, sitting there waiting for some force to move them. And so with just a little bit of energy, these electrons will move. And that's how you get electricity. Insulators are the exact opposite. So this is another kind of classifier for different types of materials. Insulators are another group. And these are materials where electrons do not easily move. So the exact opposite of conductors. These would be elements or compounds that have 5 to 8 valence electrons. So if you notice, that's a lot more valence electrons. And if you remember from chemistry, these valence electrons, usually these electron rings or shells, they like to complete sets of 8. So like shells, valence shells, complete sets of 8 electrons. And so if you have closer to that set of 8, like 5, 6, 7, or 8 electrons, these would not want to easily move. What happens more often is that they kind of like taking in the electrons to complete their set of 8. So these do not have good electron movement in them. They usually don't want to pass their electrons off because they almost have a complete set. And so some examples of these insulators would be like rubber, wood, or some of these noble gases on your periodic table. And the really cool quality about these insulators is that they're used a lot of times for protection, electrical protection. So if let's say you have this copper wire, like at home, copper wires or cabling or whatever, they usually have this kind of rubber insulation. And so this insulation is used to, when you grab onto this set of wires or cables, it's so you don't get electrocuted. And so those electrons from the conductors, that's inside these cables, they don't pass through the rubber, to your hand. And so that's one of the really big benefits to using insulators with electricity. And so a lot of times too, if you've ever seen these heavy-duty like electrical safety equipment, like rubber gloves or other things like that, that is the purpose for them. They're to protect your hands from if you, let's say, touch an open wire. They will protect your hand from getting electrocuted. It will protect your heart if the electricity passes through your entire body. So very important to understand why these insulators are used, so that you can be protected. Alright, so what is current? Well, current is actually kind of what electricity is. It is the movement of electrons, and that's really it on an atomic level. So electrons that break away from these conductors, if you give it a little bit of energy or encouragement, they're going to move, and that's what current is. Alright? If you've taken calculus, you know that or you would not be scared off by this, but if you haven't, don't worry about it. But current is technically a little bit of charge over a little bit of time. So if charges are moving, you can measure the movement, and that's just the change in charge over change in time. And the symbol that we assign current is I. So that is used, I think, everywhere, that current is represented by the letter I. Alright? So if let's say if I draw a little simple circuit right here, so if I say that this is the negative side, this is where a bunch of electrons are. So on this negative side, we have a bunch of electrons on this side. And let's say over here I have, well, the lack of electrons, so it's going to have a positive kind of charge over on this side of the terminal, right? Electron flow is the electrons are going to be attracted to this side, and so they're going to flow along the wire to the positive side. Well, that is true electron movement. So this line right here, this is true electron movement. Alright? Well, in all reality, Ben Franklin, he kind of had this brilliant notion, well, let's confuse everyone and say that current is actually in the equal and opposite direction. So I'm going to do this in blue, where blue is my actual current right here. So blue is actually going to flow this way from the positive terminal, and that's actually what I is. So red is your true electron movement. I is the equal and opposite direction as the true electron movement, which is very confusing to a lot of students. But the idea behind that is so you would reduce the amount of negative signs physicists and electrical engineers would have to deal with. So, but yes, so, and this is pretty standard at this point. It wasn't back in the day, but now it's pretty standard from the past, like, I don't know, 40, 50 years. So, yes, so current goes in the equal and opposite direction. So it goes from positive and it goes to negative. Alright? True electron movement goes from, I'm going to change color, it goes from, negative, and it goes to positive. Right? Alright, so we have different types of current as well. So one type of current that we have is DC current, and it's kind of represented right here. And DC current they're moving at a set direction with a set amount. So DC current doesn't usually fluctuate between different amounts of current. If this is time and this is the amount of current that you have on this graph, then this would be a representation of DC current. So this is a graph of DC current. All right. And as you can see, it's just kind of a constant level, and that's a good thing. You want it to be a constant level. As opposed to AC current, it actually fluctuates. So if it fluctuates direction. So if this is my current, over here it's going in one direction, and down here it's going in another direction. So in AC current, the electrons actually kind of move back and forth, and that's kind of the real difference between DC and AC, is that DC current goes in one direction, and AC current, actually the electrons go back and forth, which is very cool. And you might say, well, why do you want to use AC current? That sounds really complicated. Well, each of them have their different uses. So DC current is kind of what all of your electronics run off of. It's a very nice signal. And so, you know, your electronics, it's stable, and the components can really easily use DC current. Whereas AC has a completely different purpose. AC is used for a lot of these big electrical towers. They're used for just transporting power from your power station to your house. And the reason for that is that there's less loss with AC current, and you can easily manipulate how much current or voltage or whatever that you want to be using with AC current. DC, there's a lot of power loss whenever you're traveling large distances. And so all of these power stations, those are all the electricity that goes through these power stations are all AC. And so if you look at your laptop cord right here that plugs into the wall, you see a little square box that is attached to your that's attached to the wire that goes into the outlet and before it goes into your computer. That little square box is called a power supply, and what it does is it converts AC to DC current. And so it's very cool, and that's the purpose, is that everything that comes out of your wall is AC, and most of the electronics that we use is DC, and so you have to somehow convert it, and that little box will do it. So they have different purposes, but both are important to understand. Oh, okay, so as I said before, DC has a circuit that kind of looks like this. This is an indicator of a DC power source. And from here, if we remember, current flows from positive to negative, right? And so current would go in this direction, and it has an I associated with it. And there's going to be a set current, so it's just going to be a number. Whereas in an AC circuit, usually the AC power source looks a little bit like that. It kind of has a sine wave inside that circle. And goes like this. And this would be an example of an AC circuit. Excuse me. And an electron flow will actually, or current flow, will actually go one way and then go the other way. And so it kind of sloshes back and forth. These electrons go back and forth. And so, and that's the big difference in the notation and how a circuit looks using AC and DC. So, and this would be my I going back and forth. Alright? Alright, so we're going to kind of switch gears to potential energy and potential. And in order to really understand what electrical potential energy and electrical potential are, I'm going to talk a little bit about gravitational potential energy and gravitational potential, because the concept is completely the same, and it's easier to understand with gravity as opposed to something that I don't normally see, like electricity. So gravitational potential is basically the idea that if I hold an object up here, with some sort of mass, and and there's kind of air underneath, and I hold an object down here, right, these two masses, these have different heights. I'm going to say these have two different heights, right? And so this mass right up here, when I hold it up there, it has a larger potential to fall, right? So we say that this one would have a greater potential energy. Greater potential energy. Potential energy. Than this one. Than this second mass right here. So, and it's because it has a greater height. It has more of a distance to fall. It has more, it has more distance to fall. So, and so this is what potential energy is, and the equation for it is right up here. So, potential energy is U. It's denoted with the symbol U, and for gravity, it's mg and your y position. So if you have a greater y position, you have a greater potential energy, right? And if you notice on this equation is based off kind of two different variables. You have your mass and your y kind of your number, right? So how high it is. That's your y value. And so this equation for potential energy is based on two different variables. And so physicists thought that, maybe there might be a good way to express how much, maybe just potential something might have that's not based on mass. So if I can multiply mass in later, then man, that would be super useful. right? So I can figure out all these equations just based on position, and then just multiply whatever mass in that I have at the time later. And so that's what they did. And they denoted this potential with the symbol V. All right, so if you notice right here, V is equal to the potential energy divided by mass. So they thought, oh, let's just divide out the mass and then multiply it in later. And that's what they're doing right here. If I just solve for potential energy, in order to find potential energy, you just multiply mass times the potential. And so potential is really important to understand. Yes. If you notice too, the what's really important too, if I mention this before the next slide, the difference in potential is kind of what's important. This change in height. So it'd be the change delta H. That if you're comparing, you can only compare with potential energy. You need to compare 2 points. And that's also really important. So that works with potential and potential energy, is that it's a comparison between 2 points. Like this has a higher potential energy than this. And that's really important to understand, that because it could be relative, these are all relative numbers. And so in order to make it not relative, or a physical number, you have to compare 2 points at which you're talking about. All right? So let's basically try and compare what we just talked about, gravitational potential, energy and potential, to electrical potential. And it's very much the same idea, where again, basically electrons move from areas of high potential energy to low potential energy. So electrical potential energy is still denoted with the letter U. And again, they thought that, well, electrical potential, instead of being dependent on mass and position, or mass and the amount of energy due to position, they have instead Q instead of M. So this would be, instead of M, they're talking about how much charge you have instead of mass. And so the equation, if you can see, is exactly the same, that instead it's potential energy divided by Q is equal to your potential. Same exact idea. And so at different points, you can measure how much potential you have, and then multiply. If you want to find the potential energy, you could just multiply it by Q later. And that's what's kind of shown in this equation. All right? So just like gravitational potential energy, it's really the difference in potential energy that's really important. So you remember in the last slide, you had 2 points that I had to compare. I had at one height to another height. This is the exact same idea, that in order to really make a comparison between electrical potential energy and also electrical potential, you need to compare 2 points. And so this is the reason why voltage itself is the difference in potential from one point to another. So it is your delta V. All right? So this is actually the core reason why, if you ever have taken a multimeter or voltmeter or something that measures voltage, you have 2 prongs. That is basically measuring like one potential on one side, another potential on the other side, and then comparing them. And that's actually your voltage. So the reason why you have 2 prongs on your multimeter to measure voltage is because it's the difference in potential energy that's important. And that's what voltage is. All right? So as we just talked about, what is voltage? Well, it's represented a couple of different ways. It's represented with V, or actually this is a fancy E. It's not really like a standard E, it's a fancy E. I'm sure that's a Greek letter, but I'm not entirely sure what that Greek letter is, but I call it fancy E. And it can also, as you just learned, it can also be represented by delta V, or change in the potential. A lot of times it's abbreviated to just V though. So this is what you see most often. The units for all of these, so for voltage, voltage has units, and it's in volts. So I'm sure you've heard that as well. This is a 9-volt battery, this is a 6-volt battery. That's what it's talking about, is that's basically the difference in potential. It's your voltage. All right. So oh, and then we kind of already discussed this. I'm going to just state it again so it really makes it clear that voltage is the difference in potential, and it's a comparison between 2 points. So it's really important to understand. You cannot measure voltage by just one prong on a multimeter. You have to have two because it is a comparison. All right? So is current affected by the type of voltage? Absolutely. So if you for DC current, you're going to have DC voltage, right? Voltage is constant, okay? And if you look on an oscilloscope, so an oscilloscope is just, or oscilloscope, excuse me. If you look on an oscilloscope, it's just a way of visually representing voltage, all right? So this, on this side it would be volts, and this side would be time, right? DC voltage is just a straight line again. This is DC volts, DC voltage. And it's just a straight line. And you'll see that on your oscilloscope. It's just a straight line. But for AC current, just like AC, or AC voltage, just like AC current, if this is my voltage and this is my time, I'm going to say that this is at 0 volts. So this is my baseline. All right. You will see again that it's a sine wave, and it goes just exactly like AC current. So it's also really good to understand that AC current, if you ever measure it with a multimeter, you're actually measuring kind of like the average voltage. You're not measuring one value. Because as you can see, voltage has many different values. It can be there, it can be there, it can be there, it can be there, it can be there. So you're actually measuring the average voltage it's called the RMS voltage. Whenever you measure voltage with a multimeter, that number that you read off, that is your RMS voltage, or average voltage. All right? So if I'm going to talk about voltage, current, I have to really talk about resistance. So what is it? Well, it resists the flow of current. So that kind of makes sense, right? If something resists something, it's called resistance. So electrons are going to be flowing. Electrons are flowing this way, right? And basically resistors, they kind of make a roadblock of some sort, or a kind of increased pipeline so that electrons can't flow through there as fast, and so it resists the flow of current. All right, so actually there's resistance in all materials. So if you have some sort of wire, right, and you have electrons flowing through the wire, right, these electrons are going to bounce off things, right? They're not going to go in a straight path. They kind of bounce off things or bounce off each other when they're flowing. And so all materials actually have resistance. And that's kind of a good thing to understand as well. And but for our purposes, there are components that are specifically designed to give resistance. And you might be thinking, why would you want to do that? Why would you want to resist the flow of current? I think more power is better. Well, certain things, if you have too much, let's say if you have too much current flowing through something, like I have a bunch of electrons flowing through something, right? And your component, let's say, doesn't want that much current to go through it, like there's an amperage rating on your whatever component you have, or your light bulb or whatever, then that would be bad, right? You don't want too much power going into something, so burn out. So these resistors are designed to kind of slow down these electrons so that not as much power can go to those components, right? And so that's why they're useful. They're extremely useful. And so, as I said before, they lower the amount of current flowing through the circuit. And So the units for resistance, they're in ohms. Oops, excuse me. They're in ohms, and they are denoted with the symbol omega. That's a capital omega. And very useful in circuits. You see resistors all the time. So let's talk about how that affects kind of energy, how resistance affects energy. Well, if resistance kind of slows down the movement of electrons, that takes some energy, that takes some work to do that, right? So um, if you remember from your physics class or not, I think this makes sense though, is that whenever you, let's say, rub your two hands together and you're rubbing them really fast, your hands kind of get warm, right? That's from this friction that's happening. So it's the work kind of done by friction, and all that energy is released in the form of heat, right? Well, resistance acts exactly the same way in a circuit. So you have these electrons trying to run past, and so they're kind of getting resisted to do that. And so the energy it takes to resist this flow of current, that is released also in the form of heat. So the work done by the resistor is released in the form of heat. And that's why your computers, that's why they get hot, is that it's all of this kind of it's all this resistance, the work that's done by resistance, or the energy that's spent to resist the flow, is released in the form of heat. So your computers get hot, your iPhone gets hot if you run them too fast. That's why things get hot. So it's kind of cool. So if you had trouble understanding like really what voltage, what current, and what resistance is when I was kind of talking about maybe like the physics definition and stuff for all of these, I really hope that this water analogy really works out. So I'm going to start kind of with what current is. So amperage meaning current. So if you look at this example right here, kind of the flow of the water going down, if you think of water like you would electrons, then the flow of this water is your current. So flow of water is current in this example. All right. Resistance, if you notice over here, right, we have our resistance kind of picture. And so if something that's impeding the flow of this water or flow of electrons, that would be something that has resistance. So something with less resistance would be if the pipeline was totally free, and something with more resistance would be if there's like a kink right here in it, so there's less flow through there. All right, less of the water can flow through it, and that would be an example of resistance. Another example of resistance, if we were going to continue with this water analogy, is if there was something like when you take a shower. You know how some people, this happens to me, and this might be kind of a gross example, but I'm going to go through it anyway because it's accurate. Is if you have a resistor, would be like if you had a hairball in your drain pipe. Right? It doesn't want to, the water doesn't flow as easily. So that would be one example of a resistor. All right. And so, and then lastly, we have the voltage. And if you want to think of voltage, voltage is kind of the encouragement for electrons to move. So in this example, it would be kind of like that change in height, or water pressure would kind of be the water's encouragement to move. Well, so that would essentially kind of be the same as voltage. So it's very, very, if this was helpful, I am glad. This is hopefully the sure understanding that of your concepts. All right, so now we're talking about some power and energy. Well, power is from physics as well. It's the rate at which you're spending energy or absorbing energy. And that's true for anything, that's true for everything. That's the definition of power. But for our purposes, for electricity, power is equal to IV, or I should have said power is equal to I, capital I, times V. And so that is the definition of current. And, excuse me, that's the definition of power. and as you can see, is measured in watts. All right, and as we showed on our schematic earlier, that this is a symbol for, on a circuit diagram of an AC power source, and this would be an example of a DC power source on your circuit. This can be DC. Sometimes it's also written like this, where that's also considered DC. So just kind of know what kind of power is being supplied to your circuit. All right. So if we talk about, we just talked about some power sources and how they look on a schematic, but we didn't talk about what they actually are. Well, power sources are just something that provide power to a system of some sort. And so, and a circuit or a load. And so they can be in the form of, let's say, batteries, if you want to talk about DC kind of power sources. And those are in the form of batteries. Also, you have maybe a generator, and those can be like AC or DC. Or even something as simple as like the wall outlet, you know, that is also considered a power source. I mean, that's powering my computer right now. So that's also considered a power source. All right? And so what we call the thing that consumes that power is a load, right? So that could be in the form of a light bulb, that could be in the form of, I don't know, a motor or a servo or my computer. I mean, my computer is an electrical load on my building's power, right? Excuse me. So so that is what a load is, and as we talked about, it's the light or motor, and they consume electrical power. All right, they take power to turn on or to do whatever its function is, right? So let's talk about some passive components. I mean, what is a passive component? Well, it's a kind of component that you would have in your circuit. Components that don't require a signal in order to function. Oops, excuse me. Don't require a signal. So they work passively. I mean, that name kind of makes sense, right? Well, we kind of already talked about what a resistor was, what a resistor is, and that just resists the flow of current, right? It will slow down the flow of electrons, right? We haven't talked about capacitor. Basically, what a capacitor does is it holds energy. So you can kind of think of it like a very small battery, and that battery can sometimes also not only hold charge but discharge as well. So you can kind of control how much energy you want moving around using a capacitor. If you want to store some energy or maybe release some energy or whatever, that's what a capacitor does, and you can control it using whatever circuit design that you have. And lastly, and I think probably the most complicated, is an inductor. But on a functional level, what an inductor does is it kind of reduces it stops the change in current. All right, so if you have something, a lot of times these are used for regulators, you know, so maybe after my power supply going into my computer, let's say I'm taking power from the wall outlet, it goes through my power supply, that box that I have connected to my computer, and then I connect the power source into my computer. Well, there's probably some sort of inductor that's right in that kind of plug in order to make sure it, as a protection against like surges or something like that. Like if there's a sudden change in current, then that's kind of like the protector against it. That is one function for inductor. So that's what they do. So some active components, those kind of require power. They require signals in order to work. So these are two examples of active components. One of them is a diode, and what a diode does is, depending on its configuration, whether it's flipped one way or the other, it can either pass or block current depending on which way it's connected. And so these can be very useful as kind of like a one-way valve, kind of idea. And so let's say, you know, LED lights. LEDs, if you didn't know, stands for light emitting diode. Light emitting diode. And so these LEDs are diodes. And so if you've ever hooked up an LED with the incorrect prong, you know, like you switch the directions on your LED, it won't light. And that's because you can only have current flow in one direction through that LED. So that's kind of interesting, right? And those can be very useful, very useful. Next, there's kind of a transistor. That's another active component. And what a transistor does is I kind of think of it like a valve. Okay, so if let's say I wanted to supply power or to supply power to B, that would in a sense open up the line for current to pass through the transistor. So it's kind of like if I give this prong right here a little bit of power, then it opens up the line in order for electrons to flow through the main line. All right, so it's like it opens the valve of this transistor. So if you think about that for a second, you will realize, oh man, that can be used as like a switch, and it is used as a switch. So if you don't apply power here, then there's no flow that goes through from here, right? If you do apply power, then there is flow through there. So you can definitely it can act as like a electronically controlled switch, right? The other purpose is that one of the cool aspects of a transistor is that the more power that you put to B, right, on this prong, actually it opens up this valve wider and wider and wider. So if you don't put a lot of power there, then you have a little bit of power flowing through the transistor. But if you put a lot of power or voltage and current going through there, then it opens up this valve very, very wide, and it can allow a lot of power to go through. So it can act as well like a amplifier. So this is also used to amplify signals. Transistors, if you've ever looked at like preamps or anything for your like guitar amps and all of those all have transistors in them in order to amplify signals. So it's pretty cool.